Welcome to the fifth of 6 webinars focusing on effective mathematics teaching. My name's Tracy Hughes-Butters and I will be facilitating the webinar, which has been designed to consider student errors in the PAT mathematics assessment, focusing on patterns and algebra and what we as teachers can do to support our students to ensure that they are able to demonstrate their mathematical skills and knowledge competently and confidently in unfamiliar situations. Now, from the PAT Maths data, there are 5 areas of concern that have been highlighted for our students in Catholic schools nationally. Please note they are not in any order. This webinar will focus on the 4th dot point, Patterns and Algebra. There are 4 examination style questions that we will unpack. Each question targets a different year or stage level. Now, please note that the last 2 questions are similar in the type of pattern used, so I would encourage you to complete both. Here is the learning intention and success criteria for the webinar. Please pause and read. Now, we need to note that we cannot effectively cover everything in a half-hour webinar. So we will draw from the PAT Maths data and analyse a series of sample questions that are similar to the questions that had the lowest achievement rates nationally. The sample questions vary from years 1 to 6. I will lead your team through a set of focus questions, and there will be plenty of time for discussion and reflection. The 4 focus questions that will prompt discussion and reflection include: Focus question 1, to ensure that we, the teachers, understand the key concepts and skills that the question is actually assessing. Focus question 2 is to consider the prerequisite knowledge and skills that our students must have in order to attempt the question. Focus question 3 is to consider why our students may have decided on an incorrect answer due to common errors or misconceptions, but we will apply Newman's analysis where appropriate. Focus question 4. What could we ensure our students experience in their learning so that they are able to experience success in this style of question? Now, I will present 4 multiple choice questions in the webinar. Simply fast forward to the year or stage level that you would like to analyse. Now, I would recommend that you complete at least 2 questions in the time and not just target the questions that your students would be attempting. We need to know the big picture, not just one part. Ensure that someone is scribing. I would recommend a whiteboard with different coloured pens. Discuss and add to the board as you work through each focus question. And when you're finished, take a picture of the whiteboard and recommence the video. Now, if you have not heard of Newman's error analysis, here is a quick summary. The analysis breaks down the 5 steps involved in solving a mathematical word problem. We start with reading and decoding, where the student reads the problem and decodes the words and symbols. The next step is to comprehend. Does the student make sense of what they have read? Transforming, where the student mathematizes the problem, that is, works out what mathematics needs to be done. Processing, demonstrating what to do to get that answer, and finally encoding, recording their final result appropriately. Well, let's begin with an example of a question targeting stage 1 or year 2, determining the missing number in a 2-digit addition number sentence. Note that only 55% of the candidature were successful in attempting a similar question. Carefully read the sample question. Pause the video for approximately 5 minutes to consider and discuss the focus questions. Ensure that someone is scribing, and when you are finished, recommence the video. Well, welcome back. The key concepts and skills that this question targets is recognising that both sides of the equal sign are of equal value, interpreting a number sentence when the addend is missing, and finally using strategies such as subtraction, counting or partitioning to find that missing addend. So what are the prerequisite skills and knowledge for this question? Well, understanding that equal sign, subtraction strategies, addition strategies, and adding both 1 and 2-digit numbers. So let's work through each distractor in this question. Well, 3. possible misunderstanding of place value. So instead of adding 30, students have added the digit 3. 30, of course, is the correct answer. 35. Well, students may have made an error in the algorithm. Maybe lost track if they were counting on. They may have added the correct value of the tens, but the incorrect values of ones by including the 5 from the original 35. Or they may think when a number is being added ends in 5 and the answer ends in a 5, then the addend must also end in a 5. 100. Well, a complete misunderstanding of the format of the question, so they've added all known numbers. Please pause the video and discuss. So based on the analysis of this question, I would suggest the following. Firstly, students must have a deep understanding of that equals sign and what it symbolises. Now, unfortunately, students often have misconceptions about the meaning of an equals sign. They tend to see the equals sign simply as an instruction for an answer. So when presented with an equation or open number sentence such as this, students cannot make sense of the question, and they may think the answer is 25 because you add all the numbers. This type of equation can be confusing because the unknown is on the left-hand side, and we're always getting questions where the answer is on the right-hand side. Students must experience and investigate these types of equations to ensure understanding of that equals sign. So what does the equals sign mean? Well, let's use concrete materials to investigate the concept of equals. In this case, coat hanger equations. Put your students into pairs. Give each member of the pair a number card from a pack of number cards and let the students calculate their total. Now, the pair needs to find another pair of cards in that pack with the same total on their cards, different numbers. They check they are correct by using clothes pegs and hang from a coat hanger. Students then record the equation when they are satisfied with their justification. Now, throughout this activity, the power of the learning is in the discussion. Students need opportunities to develop their understanding of that equals sign by sharing their thinking with others. They must understand that the equal sign means equal to or the same as, rather than makes or gives. Now, the sign denotes that both sides of the equal sign represent the same quantity. Now, a common misunderstanding among students is that the equal sign indicates that a number operation on the left-hand side is to be performed, as when using a calculator. Thinking that the left side of an equation always has the working and the right side has the answer, and only being familiar with the equal sign indicating where to write the answer is very problematic. So, working with equations such as 2 times 5 equals 6 plus 4, and concrete materials helps to develop the understanding that the same quantity is shown on both sides of the equal sign, rather than one side showing an instruction for an operation and the other the answer. Representing number sentences using concrete materials can enable students to understand the format of the equation. Consider this example. We know that both sides equal the same amount. Why? Because we have an equal sign between them. How can we represent this using concrete materials? The concrete materials clearly illustrates that the equation is unbalanced. It's unequal. So what do we need to add to the left-hand side to make both sides equal? Students should make a conjecture about the unknown value and then test, or they could simply add pegs until balanced. Either way, they will see that to make the equation balanced, the unknown must be 11. Firstly, ask students, what are we trying to find in this question? Will the answer be larger or smaller than 31? How do you know? Get them to make conjectures. Now, representing the equation in a pictorial format, let's use a number line with strips to represent the equation. Well, what do we know? Well, we know that part of the equation is 12. So cut a strip to represent 12 and mark it on the number line. What else do we know? Well, we also know the whole is 31. So cut a strip to represent 31 and again mark it on the number line. The unknown part is now clearly represented and can be highlighted using brackets. Students can now calculate the value of the unknown by either counting or subtraction. Presenting the equation in a different order. So here we have the whole. The next value we have is a part. We can see the unknown, and you can use a strip to represent the unknown if you want to. And then finally, let's find the value of it. Now, a common misunderstanding among students is that the equal sign indicates that a number operation on one side needs to be performed, as when using a calculator. Now, working with equations such as this helps to develop an understanding that the same quantity is shown on both sides of the equal sign, rather than one side showing an instruction for an operation and the other the answer. So let's represent the left-hand side and then the right-hand side. And of course, you could present it in reverse. It still demonstrates that both sides are equal each other. When your assessment for learning indicates that your students have a good understanding of the equal sign, then use these prompts to see what number sentences students can generate. The power of the learning is with the students proving they are correct using either concrete or pictorial resources. Well, here's an example of a question targeting Year 3, Stage 2. It's focusing on solving a simple proportional reasoning problem, but only 38% of the candidature was successful in attempting a similar question. So carefully read the sample question. Pause the video for approximately 5 minutes to consider and discuss the focus questions. Ensure that someone is scribing, and when you're finished, recommence the video. Well, welcome back. Let me present my thoughts on each of the focus questions. So let's start with focus question 1. The key concepts and skills necessary to successfully answer this question include, well, working flexibly with a range of 2-digit numbers. Also, working flexibly with addition, subtraction, and multiplication. Understanding halves and doubles, with twice meaning double. And recognizing that when one part is double another part, then there are actually 3 parts to consider overall. Students often misunderstand and think that there are only 2 parts overall. Prerequisite skills for this question include subtraction strategies, multiplication strategies, addition strategies, and interpreting word problems. Now, working through each distractor in this question and applying Newman's analysis, 30, of course, is the correct answer. 45 would be a comprehending error. Likely have calculated, well, twice 45 is 90, or divided by 2 as there are 2 colours of hens. 60, well, reading, decoding, or an encoding error. Giving the number of white hens rather than what the question actually asked for, the number of brown hens. And 180, a comprehending error. Likely error is twice 90 is 180. Pause the video and discuss the slide. So how can we ensure our students have an entry point to word problems? So what strategies have you provided your students to successfully access the structure of the mathematics in the problem and to select the appropriate mathematical operation in order to solve word problems? Pause the video and discuss. Well, welcome back. Typically, students are taught a variety of strategies for word problems, including draw a picture. But this usually entails drawing objects. It's not an efficient strategy because students cannot transfer their understanding of the mathematics to other word problems with different objects, or the problems include large numbers of an object. So what is needed is a representation of these objects with a basic shape, such as a rectangle, that enables students to see the number relationships rather than focusing on the objects of the problem. Now, rectangles are really useful because they're easy to draw and they can display proportional relationships. So let's consider how our students could unpack the information in this question by using a pictorial representation, a bar model. So the first question is, what's the basis of the unknowns? And that's the brown hens. We know that the white hens are double the brown hens, so let's represent those brown hens using a rectangle. Don't know the size? We just represent it as a unit in rectangular form. Now, we also know that there are twice as many white hens as brown, so we will need 2 units for our white hens. We also know that there are 90 hens altogether. Notice how visually clear this word problem has become. So 1 unit, the brown hens, is the unknown. We can see from our diagram that 3 units totals 90. So 90 divided by 3 will give us 30, which is 1 unit. So there are 30 brown hens. Now, the application of the bar method in word problems is a very effective problem-solving strategy that uses part-whole or comparison models to represent the quantities given in word problems. The visual representation shows how the known and unknown quantities of the problem are related, and they can make the word problem more accessible. The use of a unit represented by a rectangle rather than the drawing of items allows the transfer of the process to other word problems, not just problems with hens. So this method needs to be taught and practiced and valued to ensure your students apply it successfully. Now, the next 2 questions, one for Year 4 and the other one for Year 6, are similar in their focus, figurative growth patterns. The concern is that though the questions are similar, our students struggled in both year levels, and in fact, our oldest students in the Year 6 test were even less successful. So in the PAT Maths assessment, only 46% of our Year 4 students were successful in attempting a similar question, the continuing of a number pattern shown visually. Repeating patterns offer a way for students to find generalizations within a pattern by finding what comes next or what part repeats, which is known as recursive thinking. Now, this supports additive thinking, and it's the basis for developing an understanding of mathematical structure. Pause the video, carefully read the question, and then consider and discuss each focus question. When you're finished, recommence the video. Well, welcome back. Now, the key concepts and skills assessed in this question would include interpreting a figurative pattern involving a constant increase, identifying how an element in a visual pattern is related to the preceding element and the subsequent element, and finally, applying effective addition strategies such as counting on. The prereq skills and knowledge would be skip counting from any point, forwards and backwards, and counting collections. Well, let's work through each of the distractors using Newman's analysis. Well, 13, it's a processing error. Students may have miscounted the number of shapes in the pattern and counted the number of toothpicks in the 4th shape. It's quite a common error. 15 is a transforming or processing error. Students may have drawn the 5th shape and miscounted or misrepresented the number of toothpicks needed by 1. 16, of course, is the correct answer. 20 is a transforming error. Students may have thought, well, 4 toothpicks in the 1st square, so 20 toothpicks in 5 squares. 39, another transforming error. They may have multiplied the number of toothpicks in the previous shape by 3 rather than adding 3. Pause the video and discuss the distractors. When students search for structures and rules underlying patterns, they are beginning to engage in algebraic thinking. Now, this is the basis for the formal algebra learned in later year levels. So allowing time to construct and consider patterns is fundamental in student understanding and making sense of the pattern. So always encourages students to make a conjecture on the pattern, and a conjecture is a guess or a prediction based on limited evidence. Always record students' conjectures so that they can refine their conjectures as discussion and testing occurs. You should always expect justification on the conjecture. A good question is that always true? How do you know? We want students to develop an understanding that one definitive example does not prove a conjecture, and this will develop with practice. A simple but effective strategy involves students constructing or drawing the given shapes of the pattern and then asking them to note how they would continue the pattern. And you need to be aware how your students are generating the pattern. Do not assume students will create the pattern using the same rule as you. For example, I would generate the pattern by adding a group of 3 toothpicks to the previous figure. Now, students may have a format that does not even follow a pattern. It may be a basic counting process or a process which is still mathematically correct, as this one is. This is where it is essential that class discussions happen on the different ways to generate a pattern, noting how the rule was developed and the positives and negatives of the processes. The fact is, your students may not generate the pattern the same way as you, so check. And keep in mind that some of your students may simply be using a counting process which is tedious and easy to make errors. Regardless of the process, all generators of the patterns should be considered and discussed by the class. So physically construct the pattern or draw the pattern and then complete a table to represent the growth pattern. Note that the inclusion of the second row demonstrates that additive format of the pattern, and it allows students to identify which quantity stays constant, 4, the first term, and which quantities vary, the number of 3s to be added. Now, if your students have an alternative way to physically build the pattern, then ask them to complete a table. Patterns often elicit multiple solution strategies. It allows students to think about the mathematical structure and it engages them in justifying their thinking. Now, when considering a growth pattern such as this, students may initially focus on the fact that the pattern increases by 3 each time and might express it as, oh, we just add 3 toothpicks each time. Now, this type of recursive thinking highlights the changes within one set of numbers, the numbers of toothpicks, but it does not highlight the relationship between the two sets of numbers, the position or figure number of the pattern, and the number of toothpicks at each position. However, for the Year 4 question, recursive thinking is sufficient. Now, students in all year levels should have the opportunity to work with visual and concrete representations repeatedly throughout their learning of patterns. It is important for students to initially work with concrete objects so they can make sense of the pictorial representations. Consider the pattern presented. The action of physically building this pattern, either concrete or diagrammatically, allows students to consider what's actually happening in the pattern. Completing a table may clarify student thinking by observing the pattern numerically. Considering both the configuration and the number of toothpicks for each figure, students can determine the constant, the 5, the variable, the number of 3s to add, which could also be described as a multiplier of 3. Now, the leap into formalising the pattern mathematically, the number of toothpicks needed for any figure, is beyond the demands of the curriculum at this stage, but it should not be ignored if students are capable and curious. And please note, this will be dealt with in the next question, so I would encourage you to work through it as well. Well, this is an example of a patterning question for Year 6. It is an extension to the Year 4 question, except its focus is extending a number pattern presented to describe a later shape. Only 36% of our students were successful. Things are becoming worse, not better. So pause the video and discuss the 4 focus questions. So the key concepts and skills would include inductive reasoning, where students can draw conclusions by moving from the specific to the general. That is, from the pattern values, determining the generating rule to calculate a distant term. Recognising an arithmetic sequence. Recognising the connection between the value of a term and its position in the sequence. And finally, calculating a term later in the sequence. Well, the prerequisite skills and knowledge is number sequences. Well, what would attract students to the given distractors? 24. Well, it's a processing error. Students may think that the rule is multiply the shape number by 3. They don't realise that the repeated squares have shared edges. 25 is the correct answer. 26 is a transforming error. They've doubled the 4th term to generate the 8th term. Got to give it to them. They're thinking, but it doesn't work. 32 is another processing error. They've multiplied 8 by 4 as the pattern involves squares and squares have 4 sides. Well, working with patterns can offer a way of engaging with mathematics that goes beyond the right and wrong answers of arithmetic. Patterns can elicit multiple solution strategies from your students, and it allows them to think about the mathematical structure. Working with patterns engages students in offering conjectures and justifying their thinking, but it must also be taught effectively for these qualities to occur. Now, when students search for structures and rules underlying patterns, they are beginning to engage in algebraic thinking. Now, this is the basis for the formal algebra learnt in later year levels, and it is the beginning of making sense of the world. Allowing students time to construct patterns is fundamental in understanding and making sense of a pattern. Always encourage your students to make a conjecture on a pattern. A conjecture is a guess or a prediction based on limited evidence. Always record their conjectures so that they can refine them as discussion and testing occurs. You should always expect justification on the conjectures. Continually ask, is this always true? How do you know? We want our students to develop an understanding that one definitive example does not prove a conjecture, and this will develop with practice. Well, students in all year levels should have the opportunity to physically construct patterns and reflect on the observed regularities. Working with concrete and visual patterns allows students to identify which quantities remain constant, which quantities vary, and then the functional relationship, actually describing that rule. Consider the pattern presented. The action of physically building the pattern, either concrete or diagrammatically, allows students to consider what is happening in that pattern. Completing a table may clarify student thinking by observing the pattern numerically. The second row in the table is essential as it numerically describes how the pattern forms. The table can promote discussion using prompts such as what do you notice and what do you wonder? Students will often notice that the additive process occurring in the total row. By considering both the configuration and the number of toothpicks for each figure, students can determine the constant, the 5, and the variable, the number of 3s to add, which could also be described as the multiplier of 3. Students may also notice the link between the number of 3s added and the figure number. So this leads to formalising the pattern mathematically so that they can calculate the number of toothpicks needed for any figure in this pattern. Students could describe the functional relationship as reduce the figure number by 1, multiply by 3, and add 5. Well, this webinar has certainly made me reflect on my practice. Do my students spend enough time investigating patterns by constructing them both physically and diagrammatically? Do I promote the construction of a table as a strategy? Have we spent a solid amount of time observing the connections in a table to develop a rule? And finally, do my students actually understand how important the practice and the consolidation of patterns is in developing an algebraic thinking process? Now, as I stated in the beginning, we cannot begin to triage patterns in algebra in one short webinar, but we can reflect on the following. Do our students truly understand the concept of the equal sign? Are they able to unpack a word problem and represent it diagrammatically? Do our students have time, and do they value the physical generating of figurative patterns and then deconstructing them through investigation and discussion? Do we promote and value conjecturing and justifying when we investigate patterns? And are we actively encouraging and valuing inductive reasoning with patterns? Pause the video and discuss each question with your team. And finally, did we hit the mark? Well, here is the success criteria for the webinar. Discuss them with your team. What can you employ in your classroom to support your students' learning? Thank you for joining me today.